Okay, so now that we have defined what a reduced row echelon matrix is, and we've seen why they are useful in the context of solving linear systems of equations, and now we've developed an algorithm for putting any matrix that we start with in that form. Let's connect these ideas and try and solve a system of linear equations. So here we have a system of 3 linear equations, and our variables are x1, x2, and x3. So step 1 is set up the augmented matrix corresponding to this system. So we have our coefficients in column 1, 2, 3 corresponding to the coefficients for x1, x2, x3, and then we have a column of our constants that are the right side of the equation. And then step 2 is going to be, well, let's apply this row reduction algorithm. And so again, I'm going to abbreviate reduced row echelon form with RREF. And this is a very algorithmic process. I will go through the steps of this on the next slide, but it might be good for you to practice starting with this matrix, put it in reduced row echelon form using that row reduction algorithm that we developed in the previous video. And again, the order of operations that you do this are not unique, but the end result should be unique. So I could, for example, start this process by taking this top row, and since I know eventually that I want that pivot to be 1, I can scale this by 1/2. And I'll pick up this process on the next slide, but I think it would be good for you to give this a shot on your own and then compare with the results that I get on the next slide. Okay, so here is the augmented matrix corresponding to the system of linear equations that we had on the previous slide. So I will go through a set of steps that can take this matrix and express it equivalently through a series of elementary row operations in reduced row echelon form. You may do this in a different order of operations. In the end, our final reduced row echelon form should be the same. So one thing that I can do, again, you might think about doing a different first step, and that's okay. But let me first begin by scaling row 1. So now I have a pivot that I have highlighted in red over here in the top row. So I have a pivot column, the leftmost column over here. And then what this algorithm tells me to do is once I've identified the pivot in the top row, let's eliminate the entries below each pivot should be 0. So we're going to do replacement to make that so. So I can do a replacement on row 2. So now I have a 0 here. Right, namely, I multiplied the top row by -4 and added it to row 2. And I can do a similar operation on row 3. And now what I would do, I would multiply this top row by 2 and add it to the third row. And now I have a 0 below the pivot in this first column. And now I work with the next submatrix over here. And I've highlighted this entry in blue because this is going to be my next pivot for this matrix over here. So now I'm going to repeat this process on this matrix. Mainly, I want to make sure that all of the entries below the pivot are 0. So there's just one entry over here. So my next step could be, well, let me just add these two columns, right? So that would make this 0. I take the -2 and the 3. That gives me 1. I take the -12, I add it to 14, and now I have a 2 over here. So at this stage, this matrix is in row echelon form. It's not in reduced row echelon form because this pivot is not 1, and I should have zeros above each of these pivots. So the next couple of steps are going to now take this row echelon matrix and write it in reduced row echelon form. So I can scale row 2. Now I'm going to divide everything in this row by -8, and that gets it into this form over here. And now I start with the rightmost pivot. In this case, the rightmost pivot is this one over here, and I'm going to use replacement to make all of the entries above the pivot equal to 0. So I will move over here. Right, I could go ahead and multiply this by like -1/4 and add it to the row above, and that would make this 0, and it also adjusts this. I can multiply this row by -1/2, add it to the row run, and that would give me the next 0 over here. So now my rightmost pivot is all set up. I've got all zeros above it. And now I take this next pivot 1, and I want to make sure that I do replacement so that the entry of all of the entries above that pivot, there's just one of them in this case, are 0. So that would be a replacement on row 1. And now this matrix is written in reduced row echelon form. And when I've got it in this form, right, we can see from this matrix what the solution is. And so since the matrix that I started with way up here is equivalent to the matrix down here, I know that these two matrices have the same solution set. In this case, we can see that solution would be x1 is 1, x2 is also 1, and x3 is equal to 2. And now I want to just add in one last step to this process, which is you should check your solution in the end. So we started with this system of linear equations. We set up an augmented matrix for this system of linear equations. We performed Gaussian elimination, row reduction on the augmented matrix to write it in its equivalent reduced row echelon form. And from this matrix, we can extract the solutions. But let's double check that these solutions work in this initial problem. So I'm going to go ahead and plug in 1 for x1. I'm going to plug in 1 for x2. And I'm going to plug in 2 for x3. And if this is a solution, then all three equations should be simultaneously satisfied when I plug in these values. So for the top equation, we can check when I plug in these values, I indeed get 5. In equation 2, when I plug in my solution, indeed I get -2. And equation number 3 also checks out. So now we've verified that this solution checks out. So great, we just solved a system of linear equations using this Gaussian elimination process. This system had one unique solution. On the next video, let's take a look at a different system of linear equations and see what happens when maybe we don't have a solution or maybe we have an infinite number of solutions.